Hey guys, so I apologize if things are a little bit loud right now. The fan on my computer is spinning really hard because it's trying to process the video from my Calc 1 class. That should be done in just a few seconds here. Today we're going to talk a little bit more about sequences. I want to talk about indeterminate forms and a little bit about growth rates. And then we're going to introduce the material from section 11.2, which is on series. So I did just go through and clear out all the extension requests in WebAssign for our class. And I was a little bit surprised to see how many there were. So if you haven't finished up homework from last week, please do so quickly, as soon as you can. Those are problems that you need to have a solid understanding of in order to be successful in the material that we're going to start covering this week, namely series. So if you needed more time on that, I went ahead and granted those. We're going to talk just a little bit more about sequences today. I'll show you a few solutions to some challenging problems. I think there were one or two problems actually that were a little bit challenging in that last homework. So maybe I'll go ahead and extend it to Wednesday of this week for everybody, just in case those two challenging problems were insurmountable. So I've gone ahead and done that. And then we can talk a little bit more. So of course this is Calc 2. Today is the 6th. Today we're going to talk a little bit more about sequences. We're going to cover the intro to series. And also I have a little update on exam 1. So your guys' scores were distributed pretty reasonably. I don't necessarily feel compelled to do this, but I mentioned that I might. And since I'm doing it for my Calc 1 class, I figured I might as well do it for you guys. I'm going to allow an opportunity to improve your grade on exam 1. So you can rewrite one solution, one free response solution to improve your exam 1 grade if you want to. So rather than applying a curve, because a curve really doesn't look statistically necessary, and I don't really like curves, this is the thing I will do to allow you to improve that exam 1 score. We probably will not be doing this for exam 2. I've never done this before. It's not something that I like to do. But because it was a new exam format, because there were some people who had a hard time getting everything done in the set amount of time, and because there might have been a little bit of confusion, I just wanted to give this opportunity. So today, I will be scanning and uploading my written feedback on exam 1. So I printed up all of your scans and I graded them just like I would grade a normal test. So they're full of comments and marks and things. I'll be rescanning those and uploading them for you to review. If you decide you want to improve your exam 1 score, you need to look at the feedback that I give you, right? Look at the stuff that I'm going to be uploading to Canvas for you today, and then rewrite your solution for one and only one of those problems. If you do this, I need you to, there will be a new assignment in Canvas. it's going to say it's worth 0 points. For you to upload your rewrite. I need you to include on your page, first your name, second the problem number and the problem itself, and then of course your solution and an explanation of how that solution differs from your original solution. So basically, explain to me what went wrong, right? Give me a better solution to a problem that you did not receive high marks on. Explain to me what went wrong and show me how to fix it. Also, please remember your name and the problem number. That will make my life easier. This is what I came up with as the most fair way for me to offer something like a curve to my Calc 1 class, where they had a lot of problems with the exam format. You guys didn't seem to have as many problems with the exam format, but the standard deviation on these scores is still a little bit larger than I would like to see. So I think this will allow us to tighten things up and allow people who did not have time to show me everything they knew on the test to show me a little bit more. And that way I'll be able to give you a little bit more credit. And you know, I really do want everybody to succeed and feel comfy with what they're doing. So hopefully if there's some shit that you didn't learn before exam 1, you've learned it now. And you can demonstrate to me that you have learned it. Fairly straightforward, right? Yeah, so I'll be posting an announcement explaining exactly how to do this, but it really is just this. There's no honor lock or anything like that. It's just you guys preparing in your own time an improved solution to one of the free response questions. So if you didn't get to a question, or if there's a question that went badly for you, rewrite that solution, scan and upload to this new assignment in Canvas, and I will regrade that question. Right, if you give me 2 or 3 rewrites, I'm just going to grade one of them, and it'll just be the first one on the page. So don't bother giving me rewrites for more than one question, please. Just one question. Good question. This is going to be due Friday. So we're a little bit off schedule. Of course, we're not having exam 2 this week. We are a little ways out from that still. I want to take a quick look at the syllabus with you guys. Do I have a copy of that here? No, so let me pull it here. So just in case you're getting nervous, timeline-wise, according to the schedule, we should be getting ready for exam 2, but we're definitely not there yet. We are back here still. So this week, I'm going to finish our Intro to series, and then we will talk about the first few convergence tests, integral test and comparison tests this week. The alternating series test and ratio tests will be next week, and then exam 2 will be the week after. So if you're trying to plan, expect exam 2 to come somewhere around the 20th of July, somewhere in that week, between the 20th and the 25th. All right, I don't want to waste any more time. I did see that there were a few homework questions you guys wanted to talk about. I do want to look at those. So let's jump in. there were two questions that I had in mind. Yeah, 11 we can look at. 19. Interesting. So 16 is also a little bit challenging. We can look at 9 first. So I'll copy this down. Oh yeah, no stress, Nick. Yeah, if you do want to share that, that would be neat. But no need to stress about the timeline. So here's number 9. We want to find the limit as n goes to infinity of 7 to the n divided by 1 plus 9 to the n. Did anybody solve this? Does anybody have anything they'd like to share regarding this question? So the renormalization trick will work here. If I look for the fastest growing term anywhere in this expression, it's 9 to the n. 9 to the n grows faster than anything else here. Certainly 1 does not grow at all. 7 to the n grows pretty fucking quick, but not quite as quick as 9 to the n, just because the base is larger. So if I divide top and bottom by 9 to the n, I'll have 7 to the n times 1 over 9 to the n divided by 1 plus 9 to the n times 1 over 9 to the n, like this. My numerator becomes 7/9 to the n, and my denominator becomes 1 over 9 to the n plus 1. And now the numerator on its own is geometric. This sequence is not a geometric sequence, but 7/9 to the n on its own is geometric, and there the common ratio is less than 1, so that numerator is going to 0, and then downstairs 1 over 9 to the n goes to 0, so you have 0 over 0 plus 1, which is 0. So the important thing to recall here is that the limit as n goes to infinity of r to the n is equal to, there's 3 possible cases. It's 0 if the absolute value of r is less than 1. It's 1 if r is exactly equal to 1, and it's dne otherwise if r equals -1 or absolute value of r is bigger than 1. So the 7/9 to the n goes to 0 because 7/9 does have an absolute value less than 1. And the same is true of 1 over 9 to the n. That's 1/9 to the n. So this piece and this piece both go to 0. So you get 0 over 0 plus 1, which is 0. Not too bad, right? That's fine, right? Yeah, no stress. As long as you can see everything, make sure you're still taking notes. If you try to get into this with L'Hopital's rule, it'll never yield. It'll just keep churning and churning and churning. There are ways to make it work, but it's not pleasant or obvious. This is much, much faster. So I mentioned that this renormalization trick is the way you want to do things. Yeah, L'Hopital's rule can be done here, but it's not very pleasant. The derivative of the top, so if you want to do this with L'Hopital's rule, again, I'm trying to train you out of that. But if you want to see the L'Hopital rule attack here, it looks like this. First, you have to say, all right, I'm going to swap the n's for x's, because I cannot differentiate n stuff. This is our theorem saying that you can look at your sequence as dots along the graph of a continuous function. And then if you apply L'Hopital's rule, you have to remember how to differentiate 7 to the x. You have to remember how to differentiate 9 to the x. The derivative of 7 to the x is 7 to the x times the natural log of 7. The derivative of 1 is 0, so downstairs we'll have the derivative of 9 to the x, which is 9 to the x times the natural log of 9. And then you can do it from here. From here you get lim x to infinity. 7 to the x over 9 to the x is 7/9 to the x. And then you have ln 7 over ln 9 hanging out. And just like we said up here, 7/9 to the n goes to 0, 7/9 to the x goes to 0. This is an exponential function. It's decaying because 7/9 is less than 1. So this would come out to 0 times ln 7 over ln 9, which is 0. But the L'Hopital approach here sucks for like a bunch of reasons. First, if this was negative 7 to the n, then we're screwed. We can't differentiate negative 7 to the x. Just doesn't work. Negative 7 to the x is not a well-defined function for most values of x. Secondly, you have to remember these derivatives, which are a little bit strange. I bet a lot of people forget those. And then you have to do this weird thing where you regroup the terms. It's not obvious at all. And then you still have to remember this rule, right? That if you have something less than 1 raised to the infinity, that's going to 0. So you still need the same rule. So there really is nothing nice about the L'Hopital attack here. The ideal attack is definitely the renormalization attack at the top. Both approaches require that you remember this result on geometric sequences. Wherever possible, we want to use the least machinery, right? So this one doesn't require leaning on any heavy theorems. It doesn't require any differentiation. This is definitely the nicer solution. This works. It's just a little bit clumsy. But there are some things where we need L'Hopital's rule, and one of the problems I wanted to look at is just that. Let me see, was it requested? 9, 11, 13, and 19 were requested. So that was 9. 11 is good. Ryan, we don't have a comparison theorem for sequences. So we couldn't use a comparison theorem here. And I'm glad you asked that question, because that kind of comes back to one of the things I talked about last week, that we really need to keep our theorems organized. So I have a comparison theorem for improper integrals, but I don't have a comparison theorem for sequences. So there is no theorem like that which I could apply to this problem. You might be able to do a squeeze theorem here. You could say that this thing is always bigger than 0 and always smaller than 7/9 to the n, and get at it with a squeeze theorem. But again, that's more work than is necessary. So your very first thought should always be this renormalization trick. Find the fastest growing term and divide out everywhere by that. That should always be the first thing that we try. So the squeeze theorem could work here. L'Hopital's rule can work here. But all of that is more work than is necessary. So I'm going to keep going in order here. 19 we will get to. 11 was the next one we wanted to look at. So what I want to do is find the limit as n goes to infinity of 5n minus 1 factorial over 5n plus 1 factorial. And I'll show you how to do this. This is a good problem. The idea here is to remember what the factorial is. Some stuff factorial is that stuff times that stuff minus 1 times that stuff minus 2 all the way down to 3 times 2 times 1. So 5n minus 1 factorial is 5n minus 1 times 5n minus 2, because if you subtract 1 from 5n minus 1, you get 5n minus 2, times 5n minus 3, all the way down to 3 times 2 times 1. So it's the product of all the numbers less than or equal to 5n minus 1. And 5n plus 1 factorial, that's 5n plus 1 times 5n plus 1 minus 1 is 5n times 5n minus 1 all the way down to 3 times 2 times 1. So what you notice is that this piece right here is 5n minus 1 factorial. It's 5n minus 1 times 5n minus 2, that's the next term in the dot dot dots, times 5n minus 3 all the way down to 3 times 2 times 1. Therefore, the limit as n goes to infinity of 5n minus 1 factorial over 5n plus 1 factorial is equal to the limit as n goes to infinity of, I'll write it out, 5n minus 1 times 5n minus 2 times 5n minus 3 all the way down to 3 times 2 times 1 divided by 5n plus 1 times 5n times 5n minus 1 all the way down to 3 times 2 times 1. 5n minus 1 cancels. In fact, all the top stuff cancels. 5n minus 2 is the next term in the dot dot dots here. 5n minus 3 is the term after that. So what survives is just this stuff from downstairs, 1 over 5n plus 1 times 5n, and as n goes to infinity, that's 1 over infinity, which is 0. It's good shit. And the main take home, if m is bigger than n, then m factorial contains a copy of n factorial. So that's something that you will want to remember, right? Like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial is 5 times 4 times 3 times 2 times 1, which is this piece of 7 factorial. So because 5n plus 1 is bigger than 5n minus 1, the factorial of 5n plus 1 contains a copy of the factorial of 5n minus 1. So I know that all of the stuff from 5n minus 1 factorial is going to cancel in 5n plus 1 factorial. And then I just have to figure out what's left over. What's left over is the 5n and 5n plus 1, because those are not a part of 5n minus 1 factorial. So this is a good problem, and it's got a message that we want to remember. And that is that if you have a factorial of something big and a factorial of something small, the small factorial will be contained within the big factorial. So in other words, factorials, ratios of factorials, they cancel. They cancel really nicely. Questions on this one? You're heading out? Give me 1 second, guys. You gonna run to the gym, maybe? All right, sorry about that, guys. My wonderful wife is going to grab me some coffee. Questions on this problem? I'm getting a call from my office now, sorry. Hello? Oh my God. I'm getting spam forwarded to me from my office phone. Okay, yeah, so this is how factorials cancel. They cancel very, very nicely. A ratio of 2 factorials will almost always cancel completely to where you have either 1 in the numerator and nothing else, or 1 in the denominator and nothing else. The larger factorial will always contain the smaller factorial. So that's number 11. 13 and 19 were also requested. 13 is not bad. 19 is a little trickier. Thank you, baby. Let's take a quick look at 13. Somehow nobody's asked for 16, which is definitely the hard one here. Number 6. 6, play with this for a minute. This is not terribly hard, so I don't want to spoil 6 for you. There's nothing crazy going on there. This is a special kind of sequence. I'll tell you that it is geometric, right? Notice that to go from one of these to the next guy, you're always multiplying downstairs by a 3. You're always multiplying upstairs by a 2, and you switch signs. So this is a geometric sequence in number 6. So let's jump to number 13. So we want to find the limit as n goes to infinity of the natural log of n plus 3 minus the natural log of n. How is question 19 dne instead of infinity? We'll get to 19 in just a minute. Let me go ahead and sort this guy out, and then we will take a look. So Simon says he's having trouble with number 6. Continue working on it. You will get there. It is not too hard. Yeah, depending on where you choose to start the sequence, at n equals 0 or n equals 1, there are different ways of writing the formula for a geometric sequence. So 13. I can come back to number 6 if we're really in trouble. If you try to just plug in infinity for n, then you get ln of infinity minus ln of infinity. What is the natural log of infinity? So ln of infinity is infinity. So this is infinity minus infinity, which is an indeterminate form. Hopefully you remember that from Calc 1, but we're going to talk about it a little bit more today, so if you don't panic. But infinity minus infinity is definitely not 0. So Simon, just hold on for a second, okay? We will come back to number 6, but for now, let's try and stay on the same page. The trick to getting this guy is to do a little bit of algebra. one of your properties of logarithms says that log x minus log y is log of x over y. So this is the natural log of n plus 3 over n. And then I have a theorem that says you can shove limits inside of continuous functions. And the limit as n goes to infinity of n plus 3 over n is 1. We get that with the renormalization trick. So this is 1 plus 3 over n divided by 1, which is the ln of 1 plus 0 over 1, which is the ln of 1, which is 0. So the limit of the sequence in problem 13 is 0. And the trick is really just this, just rewriting using the log rules and then shoving the limit inside. This again is something you could do with L'Hopital's rule. Once you get to this stage, you could take this limit using L'Hopital's rule, but you shouldn't, because it just is a bit of a mess and the renormalization trick does it faster. Okay, I'll jump back to number 6 really fast. So we can get that out of the way. What did I say, -4? Ooh, did I close it? Oh, baby, could I ask you to use the spare keys, the ones hanging in the kitchen rather than by the door? So the numbers vary. I'm going to use these. -7, 14/3, -28/9, 56/27, and so on. Okay, so if you choose to start the sequence at n equals 0, which I contend is the more natural thing to do, you will get a different looking formula than if you choose to start the sequence at n equals 1. And the textbook, and hence WebAssign, chooses to start the sequence at n equals 1, which is why their formulas might look a little bit different. So I'm going to go through this with the assumption that we're starting at n equals 0. Yeah, so the numbers are going to vary a little bit, but that doesn't matter. The patterns here are the big deal. So if I say A0 is -7, A1 is 14/3, A2 is -28/9, and A3 is +56/27, then what you notice is that to go from here to here, you're multiplying by -2/3. -7 times -2 is +14, and you have a 3 downstairs. To go from here to here, again, you're multiplying by -2/3. 2 times 14 is 28, -1 times +1 is negative, and 3 times 3 is 9. And the same thing to go from here to here. We're again multiplying by -2/3. So this is a geometric sequence with common ratio r equals -2/3. That much I think we should all agree on. And I think all of your common ratios should be -2/3, even if your starting value is a little bit different. So I could say AN is equal to -7 times -2/3 to the n, where n runs from 0 onwards. And this will work great. But it's not the only way to write the solution. If you want n to begin at 1 rather than beginning at 0, you could say you have -7 times -2/3 to the n minus 1. And here n runs from 1 onward. Either of these will work fine. They're just shifted versions of each other. For reasons that will become clear as we talk about series, I prefer the top guy. But your textbook happens to have adopted the convention that geometric sequences start with n equals 1, so WebAssign is looking for the bottom guy. But you see, the only difference is this little horizontal shift corresponding to this change in domain. All right, so then let's come back here. I think there were a couple other problems we wanted to look at. I would like to look at 16 with you guys, although nobody requested it. And then I think somebody requested 19 as well. So let's look at 16 first. I want to find the limit as n goes to infinity of 1 plus 3 over n all raised to the n. If I just plug in infinity, then I will get 1 plus 0 raised to the infinity, which is 1 to the infinity. This is indeterminate. If the base was a constant 1, then I would be able to say that this sequence has limit 1. But it's not. The base isn't always exactly equal to 1. You've got this 3 over n piece that's going to 1 quite slowly. So what we need to do instead is consider this as the limit as x goes to infinity, 1 plus 3 over x all to the x. Because I'm going to do some L'Hopital's rule. This is a family of sequences for which L'Hopital's rule is necessary. So f of x is 1 plus 3 over x to the x. And if we take natural logs on both sides, you get this. This last piece here, I've brought this power, which was inside the logarithm, down front as a multiple. If you try to send x to infinity now, you'll get infinity times the natural log of 1, which is infinity times 0, which is another indeterminate form. So there's one more thing we're going to have to do before we can make this go. This is infinity times ln1, which is infinity times 0, which is also indeterminate. So finally, I'm going to take this x, which is upstairs, and bring it downstairs as a 1 over x. So my limit is lim x to infinity ln 1 plus 3 over x all divided by 1 over x. This now looks like 0 over 0. So I can use L'Hopital's rule. If I apply L'Hopital's rule, I'll get lim x to infinity 1 over 1 plus 3 over x times the derivative of 1 plus 3 over x, which is negative 3 over x squared, all divided by negative 1 over x squared. Finally, I cancel the 1 over x squared terms from the top and bottom, cancel the negatives, and you get 3 over 1 plus 3 over x, which is 3 over 1 plus 0, or 3. Therefore, the limit as x goes to infinity of ln of f of x equals 3. So limit x goes to infinity of f of x on its own is e to the 3, which means the limit as n goes to infinity of 1 plus 3 over n raised to the n is also e cubed. All right, so there's a bunch of stuff going on here. First, I relate my sequence to this function of a continuous variable. Then I notice that if you try and take the limits of that function, you still get an indeterminate form. So I start rearranging. My first rearrangement is taking the natural log. I do that in order to bring this x down because I had an indeterminate power. Taking the natural log turns my indeterminate power into an indeterminate product. To get this into a place where I can do something with it, I need to turn it into an indeterminate ratio, because that's the sort of things I can apply L'Hopital's rule to. And the trick to doing that is saying, oh, well, multiplying by x is the same as dividing by 1 over x. So I rewrite x times ln 1 plus 3 over x as ln 1 plus 3 over x divided by 1 over x. Now, as x goes to infinity, I'm getting 0 over 0, which is something I can L'Hopital. And when I L'Hopital it, I get this stuff. So the derivative of the natural log is 1 over the inside times the derivative of the inside. And the derivative of 1 over x is just negative 1 over x squared. I can cancel the 1 over x squareds, cancel the negatives, and that simplifies to this, just straight algebra. And then this limit is easy to take. 3 over x goes to 0. This piece goes to 0. So I just get 3 over 1, or 3. So the limit not of my function, but of the natural log of my function is 3, which means the limit of my original function is e cubed. And that original function's limit has to be the same as my sequence's limit. That's by our theorem. So our sequence also goes to e cubed. I have a supplemental problem for you related to this one. So in your own time, prove that the limit as n goes to infinity of 1 plus a over n, all raised to the power of bn, is e to the a times b. You can use this freely on exams. The way to remember it is to prove it. So the argument to prove this special e to the ab limit is exactly the same shit that we did here. Just instead of a 3, you write a, and instead of 1n in the exponent, you'll write bn. And everything will come out very nice. But if you go through this proof, following these exact same steps we did for number 16, you will get this formula, and you'll be allowed to use that formula on exams. You don't need to go through these limits on exams. You can just say that something that looks like this will always be e to the ab. Okay, so the last one we want to look at here is number 19. Which involves some factorial-like stuff in the numerator. Now notice what they say. They say use a graph of the sequence to decide whether the sequence is convergent or divergent. So they're not expecting you to be able to cook up this limit purely by hand. But I'll go ahead and show you what we can do. So your numerator isn't a factorial, but it's this factorial-like thing. And then downstairs you have some constant times n factorial. There really is no obvious nice way to rewrite this, but we can try our best. So the numerator is what it is, 1 times 3 times 5 times 7. It's the product of all the odd numbers up to 2n minus 1. Downstairs here I have 8, I'm gonna leave that alone, and then I've got n factorial, which is n times n minus 1 times n minus 2, all the way down to, let's say, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So I'm writing extra stuff in the n factorial to help us see what's going to happen here. There will be some cancellation. You know, the 1s cancel, the 3s cancel, the 5s cancel, the 7s cancel. The numerator only has odd things. The denominator has odd and even things. So the question is, what cancels and what survives? It's not entirely obvious. 2n minus 1 is bigger than n. So there is stuff in the numerator that survives this cancellation process. But there's going to be more stuff downstairs that survives. So it's really, there's no nice way to say this, right? And that's why they ask you to look at the graph. You know that every other term from downstairs will live. So the answer here actually, how this simplifies, depends on whether n is even or odd. So rather than doing this, let me look at a1. a1 is 1 over 8 times 1 factorial, which is 1/8. a2 is 1 times 3 over 8 times 2 factorial, which is 3 over 8 times 2. a3 is 1 times 3 times 5 over 8 times 3 factorial, which is 1 times 3 times 5 over 8 times 3 times 2 times 1, cancel the 3's, and you get 5 over 8 times 2. a4 is 1 times 3 times 5 times 7 over 8 times 4 factorial, which is 1 times 3 times 5 times 7 over 8 times 4 times 3 times 2 times 1. And again, there's some cancellation. The 3's cancel. I don't have a 5 downstairs. I don't have a 7 downstairs. So this is 5 times 7 over 8 times 4 times 2. A5 is 1 times 3 times 5 times 7 times 9 over 8 times 5 factorial. So it's 1, 3, 5, 7, 9 over 8 times 5, 4, 3, 2, 1. The 5's cancel, the 3's cancel. And you get 7 times 9 over 8 times 4 times 2. So what you notice is that the even terms from the denominator will always survive. Some of the odd terms from the denominator will cancel because you've got these odd terms upstairs. And the goal is to try and figure out who's going to get big faster, the top or the bottom. It's not entirely obvious, but if you try to graph these values, then you will be able to see. So let's do one more. A6 should be 1 times 3 times 5 times 7 times 9 times 11 over 8 times 6 factorial, which is 1, 3, 5, 7, 9, 11 over 8 times 6, 5, 4, 3, 2, 1. And again, we have a lot of cancellation, the 5's, the 3's. So I get 7 times 9 times 11 over 8 times 6, 4, 2. So I'm just going to plot these. Pull up Desmos. I wonder if I could. It probably will not play nice with the factorials now. So 1, 1/8, 2, 3/16, 3, 5/16, 4, 5 times 7 over 8 times 4 times 2. 1, 5, 7 times 9 over 8 times 4 times 2. Oh wait, let's see. 5 times 7 over 8 times 4 times 2 is good. 7 times 9. Okay, yeah, no, this is good. A5. And then A6 is 6, 7 times 9 times 11 over 8 times 6 times 4 times 2. Okay. So if we look at these first few points, do we notice any sort of trend? Well, I mean, not necessarily e to the x, but it looks like it's getting bigger. Yeah, I'm not sure if this is exponential or polynomial growth. That's a little bit hard to say. But what I can say is that the trend is that these things are getting bigger, right? They're not getting smaller and smaller. They're getting bigger and bigger. It's growing upward, and the growth appears to be concave up. So not only are they getting bigger, but they're getting bigger faster and faster. So from the graph, we can estimate or expect that the limit as n goes to infinity of 1 times 3 times 5 out to 2n minus 1 over 8n factorial is equal to plus infinity. And remember, that would mean that the sequence diverges, right? We say a sequence converges if the limit exists and is finite. Yeah, so in other words, the numerator grows faster. It does look a little bit like Florida coronavirus cases. Yeah, so the numerator here is growing faster than the denominator. So the limit is plus infinity, which means that the sequence is divergent. I'm curious now, if I entered that as a double factorial, try something interesting. That odd product upstairs has a special name. It's called a double factorial. And yeah, here you see a much larger scale graph. The limit of this thing is clearly infinity. Does it do anything else? Nah, all right. So this is good enough for us. We look at the graph and we see that it is indeed getting bigger and bigger and bigger. So I want to talk now. So the double factorial, this is a special notation. It's not something that I'm officially supposed to teach you in this class. But if you like understanding the notation, n factorial is n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. N double factorial is n times n minus 2 times n minus 4 all the way down to, it depends on whether n is odd or even, but the last few terms will look like 4 times 2. And triple factorial is like n times n minus 3 times n minus 6 times all the way down to, I guess, yeah, the last few look like 18 times 12 times, wait, what am I doing? Triple factorial, right? So my last few terms here might look like, I don't know, like 9 times 6 times 3 or something. So the number of factorials tells you how much you subtract each time. So n factorial is n times n minus 1 times n minus 2. I'm subtracting 1 each time. N double factorial is n times n minus 2 times n minus 4. I'm subtracting 2 each time. And triple factorial, I subtract 3 each time. So n, n minus 3, n minus 6, and so on. It's just a special notation for products like this, but you don't need to know this. They're called multifactorials. You can look at the Wikipedia page if you want, but I'll never use that notation on a test. I'll never expect you to use that notation. It was just a way for me to enter that into Wolfram Alpha. Okay. Indeterminate forms. We, of course, have the famous 0 over 0 and infinity over infinity. These are called indeterminate ratios. And you can use L'Hopital's rule on these. They're the only ones that you can use L'Hopital's rule on right away. And then you have things like 0 times infinity. This is called an indeterminate product. And if you want to use L'Hopital's rule on something like this, you have to turn it into an indeterminate ratio. Then there's stuff like infinity minus infinity. This is called an indeterminate difference. You've got 1 to the infinity. What else? Let me make sure I'm not missing any of these. I'll just Google. I think there's a few others like 0 to the 0. Yeah, 1 to the infinity, infinity to the 0. And this. Okay, so these guys are all indeterminate powers. So this is your full list of indeterminate forms. If you take a limit and it looks like any one of these, then you gotta do something else. The way we handle an indeterminate product is by rewriting it as an indeterminate ratio. So like I rewrite f of x times g of x as f of x divided by 1 over g of x, or g of x divided by 1 over f of x. The way you handle an indeterminate difference, this is usually going to be like multiply by the conjugate. Or other algebra tricks. Like we saw with the logarithms earlier, where you had to subtract log n plus 1 minus log n, and that gave you an indeterminate difference. The way we handled that was by using the rules for logarithms to combine into a single log, and then we were able to handle it. Indeterminate powers, the way we handle these, take logs on both sides of the expression, then try again. After applying log properties. All right. So I want to look at, we did one indeterminate power problem today. I want to look at one more, and then we're going to start introducing series. It's really dope. All right. So let's look at one more problem involving an indeterminate power. If I want to find out what happens as x goes to 0 in x to the x, first this looks like 0 to the 0, which is a problem. So instead, I can say, well, if f of x equals x to the x, or y equals x to the x, then the natural log of y is x times the natural log of x. And lim x to 0, x ln x, this looks like 0 times negative infinity, which is, so this was an indeterminate power. So we took logs on both sides to get an indeterminate product. And then finally, I can rewrite this as like ln x divided by 1 over x. I guess I should say I'm going to take the limit as x goes to 0 from the right to keep everything happy. And now this guy looks like negative infinity over positive infinity, which is finally an indeterminate ratio. And indeterminate ratios, I can use L'Hopital's rule on. So I apply L'Hopital's rule. The derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. Now I do a bit of algebra. That's negative x squared over x is just negative x. And as x goes to 0 from the right, this goes to 0. So lim x to 0 plus ln of what I want, ln of x to the x is equal to 0, which means that lim x to 0 plus x to the x is equal to e to the 0, which is 1. So I'm sorry, from here what I did is I should have written this in. Ln y equals ln of x to the x, right? So I started out with an indeterminate power. To remedy that, I took logarithms, the natural log. Then I simplify that natural log. Ln of x to the x is the same as x ln x, and I try to take my limit again. This time, instead of an indeterminate power, I get an indeterminate product, which is moving in the right direction, getting closer to something I can use L'Hopital's rule on. To turn that indeterminate product into an indeterminate ratio, I rewrite the x term here as a divide by 1 over x here, and that does give me my indeterminate ratio. So from there to here, I'm using L'Hopital's rule. The derivative of ln x is 1 over x. The derivative of 1 over x is negative 1 over x squared. If you take this ratio, you flip and multiply, then you will get something that simplifies to negative x. And as x goes to 0, negative x goes to 0. So not the limit I'm looking for, but the limit of the logarithm of the thing I'm looking for is 0. So you exponentiate to get the thing you're looking for, which will be e to the 0, which is 1. These are kind of the harder of the L'Hopital rule type problems that you'll encounter. It involves taking an indeterminate power and turning it into an indeterminate ratio. And you have to wander through those in-between steps. Okay. No, Simon, I definitely won't give you problems on a test that require Desmos. That would be cruel, because of course you're not allowed to use Desmos on a test. So all the stuff I give you on a test will be things you can handle barehanded. I do want to start talking now. Well, I guess there's one other thing. One last little topic from 11.1. Oh, what's the right way to say this? Is that good enough? Yeah. Okay. If Q and P are positive and B is bigger than 1, then, so this is the last little kind of thing I like to talk about when we talk about sequences. Logarithms are slow growing. Even logs of any powers are slow growing. Even any powers of logs of powers are slow growing. Logs grow very slow. Power functions grow faster than logarithms, but slower than exponential functions. And exponential functions get beaten by factorial functions. So here b is bigger than 1, so that this geometric sequence or exponential function is a growing exponential, not a decaying one. And n and q, sorry, not n, p and q are just positive numbers. The less than notation means an is much, much smaller than bn, in the sense that the limit as n goes to infinity, an over bn is 0. This is another fact that I will allow you to use freely. So for example, the limit as n goes to infinity of 2 to the n over n factorial is 0, because 2 to the n is less than n factorial. You can go through and prove each of these. I'm not going to, because I don't think it's a good use of your time. It's not especially enlightening. I do recommend that you remember it. So a log of any power is slower growing than any power function, is slower growing than any growing exponential or any growing geometric sequence, is slower growing than the factorial. Where by slower growing, I mean if you divide the slow by the fast, you get 0 as n goes to infinity. It's a useful thing to remember. It will come up from time to time, and it will help you do some limits faster. Like this guy on his own, if you were to try and attack this barehanded, you would be in real trouble. You can't L'Hopital it because the bottom, good luck differentiating n factorial. It'll never happen. You know, I mean, it can be done, but it's hugely complicated and involves the gamma function. The derivative of 2 to the n you could take, but you won't be able to find the derivative of the bottom, so you wouldn't be able to L'Hopital this. You would need to come up with some sort of very careful algebra argument. And while one does exist, it is not an easy one. It's much easier to remember that b to the n is less than n factorial. And yes, you can use this on a test. Right, so just like the e to the ab limit is a special thing regarding sequences that I recommend you memorize, this is a special thing that I recommend you memorize. It's just kind of classifying functions according to how fast they grow. Classifying sequences according to how fast they grow. Okay, so on to 11.2. 11.2 is the start of our discussion on series. Daniel asks, do we need to say why? Do you need to include this if you're using it on a test? Yes. If you're going to cite this, you need to at least tell me which part of it you're using. So the because 2 to the n is less than n factorial, that would be necessary in order for this to be a valid solution on a test problem. Okay. So 11.2. 11.2 is about series. Series are a way of integrating a sequence. That's how I would like you to think of these. Series are integrals of sequences. If I have some sequence here and its graph looks like this, maybe there's A1, there's A2, there's A3, there's A4, and so on. You might say, how the fuck do I talk about an area underneath this? Each one is a dot. Each one is like infinitely narrow. But I can form some rectangles, kind of like Riemann sums. So if this was A1, this was A2, this is A3, this is A4, then the area of this first rectangle is A1 because the width is 1 and the height is A1. The area of the second guy is A2, the area of the third guy is A3, the area of the fourth guy is A4, and so on. So given a sequence, AN, can we integrate from n equals 1 or wherever to n equals infinity? It's like an improper integral. I want to know what's the area under all the rectangles as you go on and on and on and on forever. Such an object is called an infinite series. Denoted, you know how you use a big S for the integral symbol, right? It's like a really tall stretched out S. Well, if you use a really tall stretched out Greek S, that's called a sigma. So he takes the place of your integral symbol. And just like your integral symbol normally has bounds like 1 to infinity or whatever, here your sigma has bounds from 1 to infinity. The lower bound might not be 1, it could be something else. And the basic idea is that sigma n from 1 to infinity of an equals all the rectangular areas from n equals 1 to n equals infinity under the graph of the sequence an. Of course, this could be infinite. This might not be finite. And so we have a question again of convergence. But this is the very basic idea. Now what's going to follow is a whole lot of technical shit. We're going to need a definition of convergence, which means we're going to need something kind of like improper integrals. I'm going to need some way to write this as a limit of finite things. And then I'm going to develop a bunch of tests, a bunch of criterion that I can check for a given series to see whether or not it converges. But the first thing you need to do is get comfy with the definition. So really what we're trying to do here is add up infinitely many things. So first, some notation. The capital sigma notation is something you should be familiar with. It just means take whatever is in here and add it up over the range specified here. So I would read this as the sum from n equals 1 to 5 of an. That would be a1 plus a2 plus a3 plus a4 plus a5. So for example, sigma k equals 2 to 4 of 1 over k would be 1 over 2 plus 1 over 3 plus 1 over 4. Or sigma from I equals 1 to 6 of e to the I would be e to the 1 plus e to the 2 plus e to the 3 plus e to the 4 plus e to the 5 plus e to the 6. This is what the capital sigma notation means, as long as the upper bound here is finite. All right, So here is kind of everything I can get in this space. So I'll give you a second to write this stuff down. Do you see that if I add up these rectangular areas, it would just be A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7, on and on and on forever. How are we doing on time? Are we out? Oh yeah, we're just about out. So I'm going to give you one last thing, and that's the definition of the infinite series. It's very much analogous to improper integrals. The sum from n equals 1 to infinity of some sequence an is defined to be the limit as some other variable, I'll use capital N, goes to infinity, of the sum from little n equals 1 to capital N of a little n, which is the limit as capital N goes to infinity of A1 plus A2 plus A3 plus all the way out to AN. We call the finite sum, the sum from 1 to n of a little n, Sn, S sub capital N. This is called the nth, the capital Nth partial sum of the full series, sigma 1 to infinity an. So the full infinite series is defined to be the limit of its partial sums. And the partial sum is just a finite sum. Just like your integral from 1 to r, you have the sum from 1 to capital N. And then if you want to know what is the full series all the way out to infinity, you find a formula for this and then send capital N to infinity. So S1, it's important that you wrap your head around the differences between the S's and the A's. S1 is A1. S2, though, is not A2, it's A1 plus A2. S3 is A1 plus A2 plus A3. S4 is A1 plus A2 plus A3 plus A4, and so on. So this is where I am going to stop us for today. I'll go ahead and actually, I should say what it means for the series to converge. We say that the full series, n equals 1 to infinity of an, converges if the sequence of partial sums that is the sequence Sn is a convergent sequence. We say the series sigma n equals 1 to infinity an diverges if the sequence Sn is a divergent sequence. So the whole game to understanding infinite series revolves around understanding sequences. If you want to construct an infinite series, you must first rewrite it as a limit of a partial sum. And then that partial sum determines a new sequence called Sn. If the sequence Sn is convergent, then the original series is said to be convergent. If the sequence Sn is divergent, then we say the original series is divergent. Yes, so I would warn you against mixing little n's and big N's. I always like to use a big N for Sn because we use a little n for the index on An. Your textbook does precisely the thing Simon is doing in chat there, using a lowercase n for the index on the partial sum and on the original sequence. While it is not strictly speaking wrong to do so, it invites confusion. So I recommend using a capital N for your sequence of partial sums. But yeah, the full series is the limit as n goes to infinity of Sn. That's the idea. So I will pick it up here on Wednesday. We will start talking more about series. I'll show you our first few convergence tests and big results on infinite series, and we will go from there. The homework from last week has been extended just to the end of this week, so you can finish that up. And then today I will be opening up a fresh homework for you guys to begin on this week. Also, keep an eye out for that Canvas announcement where I'll explain the exam 1 question rewrites if you want to, but don't begin the rewrite until you've gotten the written feedback from exam 1, which I'll be scanning in this afternoon. Nicholas asked if I have office hours on Wednesday. Yes, yeah, I'll have my normal office hour both today and Wednesday. Of course, yeah, it seems like the thing to do for now. Okay, so I'm gonna go ahead and sign out here so I can get ready for the office hour. If you guys wanna chat some more, you can come meet me over there. That is it. Alrighty, I hope if I don't see you in office hours, you have a lovely rest of your day. If you get stuck on anything, please do come by the office hours so we can chat. And otherwise, I'll see you guys on Wednesday.